climate and environment. So in that context, I would like to call up from India, giving us an overview over the Indian Thorium program. And now I have a big problem. I know that the laboratory is pronounced BARC, but I fear that I will not very well pronounce your name. Palipatu Krishnan Vijayan. If you would be so kind and show up, you are there. And please do respect my signs, which I will give you, that we can discuss.
Thank you, Chairman. So we begin a new lecture on the overview of Thorium program in India. At the outset, let me thank the organizers for giving this opportunity. Originally, Dr. R.K. Sinha was supposed to make this presentation, but unfortunately he could not be here. Well, this shows a brief outline of my presentation. I give an introduction to the thorium fuel cycle and its relevance to the long-term Indian nuclear power program and its advantages and challenges. Most of it was already covered. Maybe I can be quick there. And the past Indian experience with the thorium fuel cycle, and I also will give what we want to do in the near future, and then some concluding remarks. Well, this has already been told. So thorium is almost 4 times more abundant than uranium in the Earth's crust. It is easily exploitable compared to uranium. And India has a very large reserve of thorium in the beach sands along its southern and eastern coastal areas. Well, the long-term Indian nuclear power program takes into account this resource position, that is large reserves of thorium and modest reserves of natural uranium. As you may be aware that we follow what we call a 3-stage nuclear power program. And in the first stage, we basically use the natural uranium that is existing in what we call pressurized heavy water reactors. And if you use that, our energy capability is of the order of 300 gigawatt electric year, which is roughly 16 months of electricity generation at the current rate what India produces. Well, if we use an open fuel cycle, that is the end of our natural fissile inventory. But if we start reprocessing it and use the plutonium and the depleted uranium in fast breeder reactors initially, and later on also introduce thorium, and in this way we can enhance our energy capability to about 42,000 gigawatt electric years, which means something more than 200 years of electricity at the current level of generation. And the uranium-233 that we produce, if we use in our third stage, which is basically using uranium-233 fuel thorium reactors, then our energy capability is about 155,000 gigawatt electric year, which is roughly more than 750 years. So this basically gives the status of the different stages. In stage 1, which is well underway, we have 18 natural uranium pressurized heavy water reactors operating, and another 4 into 700 megawatt electric under construction. Several others are planned. And as part of stage 2, we have a 40 megawatt fast breeder test reactor operating since 1985, and a 500 megawatt electric PFBR, which is under construction. Actually, this photo shows that, and almost 95% of this construction is complete. And as part of the third stage, well, we have a research reactor using uranium-233 operating. It's probably the only one in the world at the time using uranium-233. And then we propose to build this 300 megawatt electric ASWR, which is has already undergone pre-licensing safety appraisal by AERB. And of course, as you know, that this stage has a very large energy potential, and towards the end, we will, we are evaluating this MSBRs, which is probably the mainstay of our third stage. Well, this is a restatement of what we said earlier. So we have the red line, the red portion of the graph shows what the PHWR program can accomplish, say typically about 10,000 megawatt electric. And if we switch over to plutonium, uranium fast-breed reactors, then we can enhance that capability to about, say, slightly less than 300 gigawatt electric. And with the introduction of thorium, say somewhere around 2045, we could actually enhance further this energy potential or our generation capacity to about 600 megawatt electric. And large use of thorium-based reactors is expected only beyond 2070. Well, on the other hand, if we short circuit this, that is, if we bypass the plutonium, uranium fast-breeder reactors and use the plutonium only in thorium-based PHWRs and molten salt reactors, then our energy capability is significantly reduced to about 36 gigawatt electric. And so this is the summary of our case study with indigenous resources. It shows that premature deployment of thorium leads to suboptimal use of the indigenous energy resource. And it is necessary to build up a significant level of fissile material before launching thorium cycle in a big way during the third stage. Well, incorporation of thorium in the blankets of metallic fuel fast-breeder reactors can take place after significant FBR capacity has been built up, which is supposed to happen somewhere around 2045, and full core and blanket thorium fast-breeder reactors only after uranium shortage is felt. And in a big way, thorium-based reactors are expected to be deployed beyond 2070. But as already you know that it's not possible to start from scratch these thorium-based reactors in 2070. You have to develop the associated technologies. So we have started this ASWR program. In fact, Dr. Anil Kakodkar, he himself has started this program. So we can call him the father of this ASWR program. And we plan, as per our current schedule, the commercial operation of this reactor is expected in 2022. And we also believe that the surplus U-233 that is produced during the operation of the fast-breeder reactors could drive the HTRs as well as the MSBRs. Well, coming to the important attributes of and advantages of thorium fuel cycle, this is something which has been several times mentioned. Okay, so I can very fast go about it. Well, thorium is thorium oxide is relatively inert and does not oxidize further, unlike uranium dioxide, and does not react with water. So this is what this, even in case of fuel failure, it will not, the system can tolerate some amount of fuel failure. So if you look at this, you find some voids created in case of failed UO2, whereas here practically no void is created. And as already mentioned, okay, high thermal conductivity and lower thermal expansion coefficient, which results in less fuel temperature, as well as it also improves the dimensional stability of this fuel. So as you can see that the irradiated fuel, thorium-based fuel, has less breakages compared to the uranium fuel. And also fission gas release rate is 1 order of magnitude less, and good radiation resistance and dimensional stability. Well, this is again another graph which has been told several times, which, okay, basically uranium-233 has a high eta value, which means the number of neutrons released per thermal neutron absorbed is of the order of 2, right over a wide range of energies, starting from thermal energy to epithermal energy, and that makes it a potential candidate to use in thermal breeders. And this is also some of the other advantages of uranium-233 compared to other fissile nuclei. That is, it has got a very low capture cross-section, and the fission cross-section is comparable to the others, and leading to a very high ratio of fission to capture cross-section compared to other fuels. And again, the thorium has typically a thermal neutron capture cross-section of about 2.5 times of uranium-238, which is good in reactor, which actually it makes more absorption in the fuel rather than the. Well, again, this has already been told. So it has got intrinsic proliferation resistance because of the high energy gamma that is emitted by one of the intermediate products that form because of N2N reaction. This has also been talked about. See, thorium has a greater energy advantage, especially if you are going for very high burn up. And by virtue of being in the lower regions of the periodic table than uranium, it produces less minor actinides compared to. Well, in spite of all these advantages, which has been mentioned over and over, we find less of thorium-based reactors worldwide. Now let's look at what are the challenges that needs to be addressed in a big way if thorium fuel cycle is to be accepted. So first of all, although the melting point, high melting point is good inside the reactor, it offers some problems while you fabricate the fuel, especially you need to add some sintering aids if you want to reduce the sintering temperature. And also, again, some of these characteristics that although thorium oxide is more inert, is good inside the reactor, but then it is not so good while we are reprocessing. And of course, these are issues. I believe that, because I'm sure that some of my colleagues like Dr. Vattal will not agree to this because he has already solved this problem. So, but still, this is what people talk about. Then, again, the intrinsic proliferation resistance also leads to problems in fuel fabrication. You have to use remote and automated techniques for fuel fabrication. And the protactinium-233, which forms as an intermediate, has high half-life, needing longer cooling times. And also we need to have separation of this protactinium. And the other problem that is challenging to this adoption of thorium cycle is the lack of experience with thorium fuels, especially if you are talking about very high burn. Now, there are large amount of global experiences already based on thorium fuel cycle reactors, starting from the US molten salt and AVR and HTGR in Germany and many others. However, these are all almost 3 decades old, and because of our special interest in thorium, our work on thorium was continuing right from the 60s, and we have mastered all technologies right from mining, thorium extraction, pellet production, fuel fabrication, irradiation in research reactors, in power reactors, and then post-irradiation examination, reprocessing, and reprocessed U-233 has been used in a few reactors already. And of late, we have also established what we call this ASWR critical facility. Well, right from the 60s, we have been irradiating thoria in our research reactors, and thoria-based MOX fuel pins, for the ASWR is being irradiated currently in our Dhruva reactor. We had a few thorium-based, U-233-based reactors. The first one is Purnima 2, which actually used a homogeneous solution of uranium-233 fuel, and then followed by Purnima 3, and currently only this reactor is operating. And the latest addition is the ASWR critical facility. And thoria bundles were irradiated in the blanket zone of the fast breeder test reactor. And U-233 MOX fuel is currently being irradiated in our fast breeder test reactor. We also irradiated almost 232 bundles in a few reactors, and up to a burn-up of about 14 gigawatt day per ton, producing a maximum power of about 400 kilowatts. Well, fuel fabrication is something which is already going on. We can make thoria-based bundles. We have already made for PSWRs as well as for test radiations in some of these reactors. And the reprocessing part, of course, I am sure that Mr. Vattal will be covering. Well, coming to the future program of thorium-based reactors in India. So ASWR is the one for which a large amount of work has been done in the immediate past. And we also have a high temperature reactor program, and basically, to reach the molten salt breeder reactor, which is, we believe, is the large scale thorium based reactor for our third stage. But the route to this molten salt breeder reactor is through this compact high temperature reactor and the innovative high temperature reactor. A little bit more details of this we will see, but first ASWR, which is a vertical pressure tube type boiling water reactor using heavy water moderator, and this is an isometric of this reactor, and it's basically a technology demonstrator designed to achieve large scale use of thorium. The earlier ones were all research reactors, doesn't need industrial scale production of fuel or reprocessing. So this is what is expected to achieve, and it is also provides, say, a smooth transition to the third stage of the Indian nuclear power program. It also addresses almost all issues of the advanced reactor designs like sustainability, enhanced safety, proliferation resistance, and economic competitiveness. The reactor incorporates a number of passive safety features, which practically eliminates any impact on the public domain. And these passive safety features are such that even in case of a large or long-term station blackout, the reactor can sustain for about 4 months without any operator action. And this is done much before the Fukushima accident. And the system is, the fuel cycle of ASWR is flexible enough to use LU thorium MOX or plutonium thorium MOX. Well, the fuel geometry is the same irrespective of the fuel that we are using. However, where we use the plutonium bundles and the thorium bundles are different in this case. And here also the enrichment is varying and different. Well, this is a gallery of test facilities that we have created for design validation of ASWR. Some of these are devoted to specific phenomena, whereas the major test facilities like the integral test loop and the ASWR thermal hydraulic test facility, which is coming up at Tarapur. These are basically a large-scale test reactors. Thank you. And in addition, of course, we are validating the physics design of ASWR in this ASWR critical facility, which has been established a few years ago. And coming to this Indian high temperature reactor program, so we have 3 reactors. As I said, the route to this molten salt reactors is through these 2 reactors. The first one uses LBE as the coolant, and it will operate at 1000 degrees centigrade. Second one uses molten salt as the coolant, and the third one is basically using fertile and fissile salts. And here is some details of the CHTR, which is using this LBE coolant, and its moderator is beryllia and graphite reflector. And some of the developments which we have already done is, we have been able to successfully produce these triso-coated fuel particles, albeit on surrogate material. And the technology for this carbon-carbon composite tubes, which are used as fuel tubes, that also has been mastered. Then here are these high-density beryllia blocks, which also has been manufactured. We have been successful in machining these graphite blocks, and then for high temperature applications, especially the oxidation resistant coatings, some of these has already been developed on a lab scale, but has to be commercialized. We also use this niobium 1% zirconium as a structural material, and the material has been developed. And a few thermal hydraulic test facilities for code development and validation has been established. One of them is, of course, this liquid metal loop, which is operational since 2009, and it can operate at to 550 degrees centigrade. There is another one which can operate at 1000 degrees centigrade. It has just been established. This is some details of the innovative high temperature reactor. Basically, it is meant for meeting all the energy needs of a small community. It can generate some amount of electricity. It can also produce transport fuel, and then also drinking water. And of course, the conceptual design has been done, and more details, especially this uses a molten salt. So we have now started looking at the various molten salts and how to operate them under natural circulation conditions. Some of these facilities has been established. A molten salt corrosion test facility to study the material compatibility has also been established. And here is a comparison of this molten salt fast breeder reactor and molten salt thermal breeder, where we use the fuel salts, and the main difference is that this cycle fissile inventory for metallic fuel fast breeder reactors are very high. In fact, these are not our studies, it's just from the literature. And then breeding ratio, which is practically same in more or less, and reprocessing in FBRs requires extensive clad removal and fuel fabrication. So this is some design in progress. So thank you. I'm just coming to the summary of, thorium offers a sustainable and proliferation-resistant fuel option with lower minor actinides burden. Over a period of time, indigenous technologies have been developed for all the aspects of thorium fuel cycle. And ASWR is being developed as a technology demonstrator for industrial scale thorium fuel cycle. India is also developing thorium-based high temperature reactor concepts, mainly for hydrogen production. However, large scale deployment of molten salt breeder reactors is envisaged during the third stage of Indian nuclear power program, which is expected beyond 2070. Thank you.
Thank you very much for this excellent timing within 5 seconds. So the paper is open for discussion. Please.
Can you hear me?
Yeah.
I have 2 questions. The first question, you were showing that you say that you had to wait. It's working now? Okay, can you hear me now? Okay. There are 2 questions, very short question I have to ask you. The first question, you say that you have to first to produce a large amount of uranium-233, and then once you have uranium-233, you can start making thorium reactors. But this is a total disagreement, which I showed to you in one of my transparencies, in which I shown to you that you can start with a system which is essentially MOX of plutonium plus thorium, and then you can smoothly, without any change or loss in rates, go slowly to a situation in which the system with uranium-233 is replacing the plutonium in one step. When you have, in their case, 2 steps. 2 steps for you means that you have to wait until 2070 or something in order to get your system working. They have to explain me why what I found is wrong. Because if that is the case, you don't need 2 steps, you can do 1 step. The second question, which I would like to make to you, well, maybe the second question I'd like to ask you, you say you're talking about thorium, and you're making all kind of concern about the fact that thorium is much more difficult to extract because it's against nitric acid, it behaves incorrectly. Now, this is clearly not what I say. What I say is that you can you can extract the uranium using fluorination, and I hope you know that fluorination is a perfectly legitimate system. Take uranium as a seed and take the thorium and throw it away. Because thorium is $50 a kilogram, so it's very cheap. So, and it gets slightly radioactive. Maybe one day you like to use it as a waste. But I mean, why do you have to go through a process in which you take the thorium through all these Torex, Purex, blah, blah, blah system, which is extremely expensive and extremely complicated, when you can simply take your fuel, get the uranium out by fluorination, and take everything else as junk?
Okay.
That's the second question. I need the answer to these 2 questions from you. Thank you.
First, let me address the first question. See, the question was, why do we go through this? Why don't we directly, after this, plutonium, why don't we directly use in molten salt reactors?
No, it's not molten salt. If you have a third question on molten salt, I have a comment also on molten salt. In my view, molten salt is a disaster situation because molten salt.
Let us first the first 2 questions. If not, we get mixed up. The question was not on molten salt, as you say correctly. It was why 2 steps when Carlo Rubbia advocates 1 step.
We are here to discuss things. If you don't want to discuss,
no, but I want just to discuss number 1 first, number 2 second, and number 3, which came after.
Well,
number 1.
Let me try to explain the first question. See,
is it wrong or is it right?
Yes, that is the question.
Well, as far as India is concerned, our first issue was to extend the availability of the indigenous resources. Now, why we went for this fast breeder reactor step, which is our second one, which is our study shows that it is the best option to multiply the fissile resources, that is plutonium, uranium fast breeder reactors initially, and then at a later stage, somewhere around 2040s, we start with plutonium thorium based reactors. And these two stages would help to build up enough U-233 reserves, and then we would be able to move on. This is our way of looking at our three-stage program. Now
the chemistry.
Now if we, yeah. Now if you use the plutonium in our say thorium-based reactors as part of the second stage, that I showed that, see, if you do that, the capacity which we can get is something around 36 gigawatt electric, whereas the option which you really mentioned, we didn't really investigate, basically. And as you are right on the second question, see, although I have shown that it has a big issue, but I am sure that my own colleagues, I said, Dr. Vattal will not agree that it is a major issue today. It has, as far as he is told, yes, fluorination and all, he has already solved this issue. So this is already a solved problem, but still, it is in the minds of people that this is one.
You haven't answered my question.
Well,
It's okay.
Okay, and we come back to the chemistry in the round table. One question by Krenesh.
I have a very short question, but just to comment on what was said on the reprocessing in plutonium. We have reprocessed at like 30,000 tons of fuel and recovered 300 tons of plutonium. And with this plutonium, this is the equivalent of the total nuclear energy produced during 1 year in the world. Okay? When I came from Paris to Geneva, I took the TGV. Half of the distance I made with thanks to plutonium. Okay, now my question is very quick. When your fast breeder reactor will get critical in Kalpakam, is this soon? It is within a few months, or because it's almost finished? I know, I've been there several times, and I would like just to know, it's a very simple question. When will you get critical of a fast breeder, a 500 megawatts breeder reactor? Thank you.
So the official date is next year, 2014. I believe it is July.
Okay, very good.
Okay, thank you very much for this precise information. And let's thank the speaker. Call up the next.